According to the World Health Organization, 466 million people worldwide suffer from disabling hearing loss. This means that 6.1% of people on Earth suffer from a disability that hinders their interactions with the world around them, potentially putting them in life-threatening danger even in daily situations. Statistics show that 1 in 3 elderly are hearing impaired, and 630 million people will be hearing impaired by 2030, and 930 million by 2050, which would be about 10% of the projected global population then. Hearing impairment can have a greater impact on the quality of life of individuals, more than just being able to hear. Studies show that infants can have impaired speech, language, and cognitive skill development, and very delayed progress in school. Adults will have fewer opportunities in education and the workforce due to their ability to fully communicate. And throughout life, people who are hard of hearing face social ostracism, withdraw from the world around them, and often face emotional issues stemming from their inability to properly communicate with the world around them.
The impact of hARk will be felt by millions worldwide. Not only will our solution bridge the accessibility gap between the millions who are hard of hearing, but we propose hARk as a visual walkie-talkie for those in high-intensity solutions like the military. hARk begins with the hardware. It's important to consider microphones, microcontrollers, and haptic feedback mechanisms for the user as they wear hARk on their head. On the software side, complex algorithms for sound directionality, classification, and speech-to-text need to be seamlessly blended into augmented reality. We'll explain how our solution gives a complete user experience by integrating the two. Here is the original system diagram, which has been slightly modified due to our hardware lab access. Join us as we take you step by step through our project.
The first component of hARk is the hardware. Along with the hARk smartphone app, the hardware consists of the Dragonboard 410C, which will act as the brains of our operation, MEMS microphones to take in sound from the environment, and vibration motors to provide tactile feedback to the user. The setup of our hardware included a cap that was altered to contain the Dragonboard suspended overhead, plugged into a 12-volt battery bank in the user's back pocket, 4 MEMS microphones shown in red, and 4 vibration motors placed in the same directions but at the band of the cap. We chose the Dragonboard because it has a 200 kHz sampling frequency, more than plenty for us to get real-time sound data in a wide range of sounds. And we collect this data by round-robin sampling, taking turns getting sound from each mic, where opposite mics are paired, and then plug them into the directionality algorithm. The general-purpose I/O ports on the Dragonboard connect to the vibration motors, which vibrate based on the amount of voltage we send it, and the analog ports connect to the 4 microphones to read in the inputs. We installed Linux onto the Dragonboard, which allowed us to run Python scripts on it very easily to talk to the hardware. And then we have one Python script to read the microphones, and then run the directionality algorithm to determine the direction of incoming noise. And it outputs an angle from 0 to 359. And then it takes this number and sends it to the Android phone via Bluetooth. And then we also use the number in another Python script to determine which vibration motors to vibrate and at what intensity to provide the user haptic feedback.
Once we have the audio signals from the mics, we developed an algorithm to place captions in the right place. Let's talk about the math behind directionality. This diagram shows 2 microphones A and B. We sketch a plane with the origin at the center of these 2 mics where the head of the person would be, and assume the sound is coming from M. In this diagram, we want to find alpha, the angle from the y-axis to M. We see that when the sound wave has reached microphone B, it has reached B' on its way to A. A to B' can be expressed as the speed of sound multiplied by the time difference of arrival, tau. We then use some trigonometry to solve for the coordinates of M, as well as the required angle. Doing so gives equations that also set theoretical limits on tau. Given tau, we can find the angle. Easy, right? Not so fast. Finding that time difference is very difficult, especially since we don't know the exact waveform of the incoming sound. Since we didn't have hardware labs, we simulated our algorithm. First, we determined what delays would resemble sounds coming from various angles. Then we manually delayed our recorded segments from just one mic to simulate the incoming signals. Next, we ran a 2-part algorithm to find tau. In the first part, we ran both signals through a bandpass filter with stops at 200 Hz and 3 kHz. On the filtered signals, we used cross-correlation to find the delay at which 2 signals were the most highly correlated. Of course, we anticipate difficulties moving from simulation to real hardware. Most notably, we expect issues with synchronization and the mic hardware. However, we believe the algorithm described is robust enough to adapt in such a deployment.
hARk uses a trained classifier to pick up on important sound signals from the user's surroundings. This component finds its place on the server, where it decodes the base64 encoded file sent from the app into a .wav file, which is then passed through our classifier model. A well-researched, curated, and comprehensive dataset was a priority for our classifier. Therefore, we chose Urban Sound 8K, which contains approximately 8,000 labeled sound files of about 4 seconds each. These labels encompass 10 classes of environmental sounds. hARk uses a 5-feature model that is computed for every single audio file. The first 2 features employ the MEL scale. MFCC is an abstraction of the overall shape of a signal, and the MEL spectrogram is a spectrogram taken along the MEL scale. The next 2 features are variants of the chroma attribute of audio signals that allow us to understand the pitch of a sound almost in terms of color. These features were found to be broad enough to cover all attributes of our sampled sounds, but specific enough to pick up on the differences between them. We found that by purging our dataset of some less important sound classes, our accuracy shot up from 72% to 88%. We decided to focus our model on identifying car horns, dog barks, gunshots, jackhammers, and sirens or alarms. Initial experimenting was done with classifiers such as a PyTorch k-nearest neighbors model that had problems with speed, a PyTorch CNN that was very inaccurate, and finally a TensorFlow CNN that was low accuracy too. We fixed this problem by computing and feeding in the features described before. The final Keras model was constructed from 2 convolutional layers and 2 dense layers. We employ max pooling and dropout to account for irregularities and prevent overfitting to training data. The final result we were able to achieve with our classifier achieved high accuracy in both training and testing. The diagonal seen on this confusion matrix shows that we do have a non-negligible false negative rate. Therefore, we determined that we should set a 90% threshold confidence for our classifier predictions to hold true.
Now let's talk about the speech-to-text component. There are several speech-to-text libraries out there, but for our needs, we decided to use the CMU Sphinx library. We chose this library because we needed one that met our 3 main criteria: free and open sourced, offline, meaning the processing is done on the phone, and fast, because we want the app to be real-time. We implement an algorithm called voice activity detection to detect when human speech begins, even in the presence of background noise. The state-of-the-art method is currently to move the signal to the frequency spectrum using the MEL spectrogram and then applying a recurrent neural network. This is still an open research topic and is being improved upon every day. Now that we've detected human speech, we need to recognize it. This is done by a 5-step process. Step 1 is to split the waveform by periods of silence. Then we split this period into 10 millisecond frames and we calculate 39 features from each of them. We then look at our language model and select a large set of possible words that could have been said and use a hidden markup model to calculate the probabilities of each of these words. The highest probability word is then the word that is recognized. Here, you can see a flowchart of the same process. The acoustic model is related to a linguistic term called phones, which is like the basic building block of a word. The acoustic model tells the decoder what each phone sounds like. The language model defines our dictionary or set of words that can be recognized. Early on, we used basic language models like those used for digits or weather before moving to the United States Common Words model. But this model ended up containing 4 million words, which was too large for us to handle in real time. To fix this, we wrote a Python script that cross-referenced the US Common Words model with the 10,000 most common words spoken in English and trimmed the language model accordingly. This resulted in a much faster model and still allowed us to have normal conversation. Now let's talk about the AR and the Android app. We created a multi-threaded Android app that utilizes AR core in its main thread, while communicating with the web app and recording using the mic in separate background threads. AR works using a method called structure for motion, which finds interest points and how they move between frames. To place a text without a surface to anchor it to, we utilize a phone's accelerometer and gyroscope to approximate the way the phone moves. We then place text using a quaternion matrix, which defines the translation and rotations of how to place the text. The user interface also had some decisions to be made. We decided to alert the user to off-screen text using an arrow. We keep all text on the screen for 5 seconds, and if there is an important environmental sound, it is highlighted in red. Here is a screenshot depicting someone speaking in front of the user while another person is speaking to the right of the user. You can see the arrow in the top right pointing that there is text placed off the screen to the right. Our eventual goal would be to have the AR running on specialized hardware like smart glasses. Up to the making of this video, our app runs in real time, performs offline speech recognition, online sound recognition, and uses a web app to determine the direction of sound. This is because we could not get our hardware soldered before the quarantine, so we used a server to simulate the hardware. Our original final design would be completely offline and be integrated with hardware that automatically detects direction of sound and provides AR text and haptic feedback in the form of vibration motors in the detected direction. Now, let's see a demo.
Hello there. Hello. What are you thinking?
Do you know how many people are hard of hearing?
How many are there?
300 million. Could we help them?
Perhaps.
How? Wow, everyone really is staying home.
Now that you've seen how our prototype works, let's speak a little about how to commercialize this product. We've broken our timeline down into 3 phases. In phase 0, we will complete the minimum viable product by fully integrating the hardware and software components. We predict this will take about half a year. In phase 1, we will focus on deploying our app onto existing augmented reality hardware like the Microsoft HoloLens, as well as raising seed funding. In phase 2, once we've established a working product, we can begin adapting to military and medical usage by building customized hardware, which will provide hARk with lots of potential for growth. It's also important to consider our competition. The 3 dominant players in AR currently are Microsoft, Magic Leap, and Google Glass, each with devices ranging from $1,000 to $3,500 per device. We believe that the HoloLens is ideal for phase 1 deployment and testing, since it is already being used by businesses and the military. In phase 2, our vision is to develop a product that is cheaper than the HoloLens, with hardware specifically created to provide an accurate heads-up display and directional hardware feedback, as well as software optimized for directionality, offline speech-to-text, and noise classification. With our prototype, it's possible to help out the millions of patients who are hard of hearing. In the future, we plan to enable hARk to hARk communication to direct contact between military and medical personnel, as well as underwater communication. And with that, thank you for listening about hARk, the next generation hearing aid by ECE Capstone Group 45.